Good day, everyone. My name is Konstantin Kosmack, and I am working with Professor Luca Pasquale. And today I would like to tell you a few words about my second-year activity, which was mainly related to lanthanum fluoride-based ionic conductors. And solid electrolytes are broadly used nowadays in different applications, such as fuel cells, gas sensors, different batteries, supercapacitors, but there are still some problems such as insufficient conductivity of these materials, or these materials could be easily changed its properties under some environment changes such as temperature, time of functioning, or humidity, or some other properties. To increase the conductivity of the material, it could be done in different ways. One of them is to create a multi-layer system, as you can see here. We've used lanthanum fluoride, strontium fluoride multi-layer, and as you could see here on the graph, it's clean strontium fluoride or clean lanthanum fluoride conductivity, but if we use multi-layer structure, it gives us 2 orders of increase of ionic conductivity, which is mainly related to increase of interface layers, and this interface region has got different structure. This actually gives us this increase. And lanthanum fluoride is a good prototypical system to study ionic conductivity because of its relatively simple hexagonal lattice structure and relatively high ionic conductivity values. But it's not as simple, it was not so simple to study this material because of previous year we were studied these materials with X-ray photoelectron spectroscopy technique. I will say a few words about this technique later, but this technique is only interface surface sensitive, only few surface nanometers. And to study the depths of the film, so all the thickness of the film, we were forced to use sputtering. And apparently with depths, we observed increase of oxygen inside of the film. And this was observed not only by us, there are also quite a big groups which have seen the same results. And we can ask ourselves, where does oxygen come from? And let's start from the beginning, from the how this film was made. So it was prepared in Russia with molecular beam epitaxy chamber in ultra-high vacuum. Ultra-pure material, lanthanum fluoride and strontium fluoride, was put in effusion cells. Then it was evaporated on top of the substrate, and films obtained then were studied in different ways. So by changing the substrate temperature, we could obtain really different morphology of the surface. As you can see here, it's IFM pictures, atomic force microscopy pictures, and on 400 degrees growth, we could obtain nanocrystallites of lanthanum fluoride, and actually they are well ordered, as you could see from from electron diffraction picture. On the right side, it's higher growth temperature and really different picture. Even here, you could see even fringes from lanthanum fluoride crystals, which points on hexagonal crystal structure, and also high quality and good growth parameters. These films were studied in state of art. We've got the possibility to use beam time at Soleil synchrotron near Paris, which mainly is the same as X-ray photoelectron spectroscopy, but with higher energies. So we've got high energy light beam, which goes on top of the substrate, and then electrons emitted from the surface, and we could analyze these electrons with electron analyzer, and which electron energies gives us sort of fingerprint of the material, as you could see on the next slide. Here is 3D peak of lanthanum fluoride, which got some special characteristic peak, which points us on a clean film. So during the evaporation, we prepared really clean films with no traces of oxygen on lanthanum fluoride, on silicon substrate, and also no chemical reaction between films, in between these lanthanum fluoride films and substrate. If we leave our sample under the beam for a while, so at the beginning you see the red curve, which gives us more or less the same result, so clean lanthanum fluoride film. If we increase the time under the beam, you could see changes of this film. So fluorine, we've got lanthanum, 1 lanthanum and 3 fluorine atoms on the surface, and fluorine atoms start to deplete from the surface, and it gives 3 bonds on top of it. And as you could see here, the C peak, which appeared and correspond to these 3 bonds, is slowly shifting with time, which points us on progressive oxidation. So actually, it's one of the proofs where does oxygen goes. And also, sputtering was performed, and it was quite unexpected results that after sputtering, all the surface is slightly distorted, and it's easily for beam to deplete fluorine from the surface. And as you could see here, after 8 minutes, we received a completely different picture, and there is a surface. Surface of the sample is modified, and we could observe metal clusters on top of it. So fluorine is completely depleted, and only metal clusters left on the top of the lanthanum on the top of the film surface, and all of them got 3 bonds. And as you could see here, it's progressive oxidation. And on the next slide, it also could be shown that from residual gases, even in ultra-high vacuum, the material is so reactive that it could absorb oxygen from everywhere it could take it. And it's also quite interesting. So we could perform in this way even some sort of lithography. We could change the material. So we've got clean lanthanum fluoride on one spot under the beam. And if we move it and insert some other gas, for example, or liquid, iodide or something else, we could change the material in this proper point. So this could be interesting, and it could be used. Next spot, which also is quite important, that temperature more or less gives us the same results. So fluorine lattice is not as stable as lanthanum, and with increase of temperature, you could see the shift of the peak or broadening, which points us also on fluorine loss, and its substitution with oxygen on the surface. Another really interesting and promising result was the study of multilayer structure. With this technique, we were able to obtain the results from the buried interface. So we got strontium fluoride, lanthanum fluoride underneath, and the interface gives us this peak actually here, which you could see, and this corresponds to this enhance of ionic conductivity, which I was speaking previously. So at the interface, we've got 3 bonds, 3 places for fluorine to increase the conduction. It wasn't observed previously, so we were the first who've done this. And as a side activity, I've visited Eurodas school for creation of gas sensors, to be able probably to produce something by myself in the future. And here I was able to study production, and I've actually done the gas sensor from the beginning, from silicon substrates in clean room, using lithography and some other techniques, I was able to produce this microchip with micrometer resolution. Here is tungsten oxide nanoparticles on interdigital rods. It goes on top of these rods using dielectrophoresis from the solution. And actually, I received working sensor and even working under in-room temperature. It was really interesting experience for me, and I hope I will somehow implement my experience in future work with material I've studied before. Here is a list of publication, and now we are working on the publication of the recent studies of lanthanum fluoride. So thank you for your attention. If you've got any questions.
Your cooperation involved Russia and France.
Yes, we've got a possibility to use this beamline at France synchrotron, and so and they actually said if we publish some good activity, they will collaborate more. And these guys in France, which I have where I have studied with sensor activities, they said that I can also send them some materials, and they can prepare if I haven't got equipment here. So,
okay. Which is good. Thanks again.